is Chaitra. Today, I'll be talking about theory of computations, a research paper from Springer Journal. This research paper was published and approved on 5th August 2024. Jumping automata over infinite words. This paper will be introducing and studies jumping automata over infinite words, extending the concept from infinite words. Unlike traditional automata, this read input sequentially. Jumping automata can read letters in a non-consecutive manner. For infinite words, there are three semantics that are proposed. Automata that reads the word in some order without overlooking letters. Automata that permute the word in words of a given size k. And automata that permute the word in a windows of an extensionally quantified bound. This paper examines expressiveness closure properties and algorithmic properties of these models. The jumping automata over infinite words are a powerful tool for studying the behavior of systems that operate on infinite streams of data. These systems are most common in many applications such as network monitoring, sensor data analysis, and financial modeling. By allowing jumping automata to read letters in a non-consecutive manner, we can model systems that are able to jump ahead in a time or to process data in a more efficient way. The three semantics that we propose for jumping automata over infinite words that allows us to model a wide range of systems. The first semantic is this will be allowing automata to read the word in some order without overlooking letters, that is suitable for modeling systems that need to process the word in some order without overlooking letters, that is suitable for modeling systems that need to process all of the data in a stream but can do so in any order. The second semantics which allows automata to permute the word in windows of a given size scale, that is suitable for modeling systems that need to process data in a fixed size window but can do so in any order within the window. The third semantic which allows automata to permeate the word in windows of an extensionally quantified bound, that is suitable for modeling systems that need to process data in a variable size window but can do so in any order within the window. Jumping semantics. In the jumping semantics, a word W is accepted if the automaton A accepts a permutation of it. This means accepting a word W that has the same number of occurrences of each letter as W for letters occurring finitely often and the same set of letters that occur infinitely often. This semantics enables reasoning about the relative quantities of resources in an ongoing process. This will be distinguishing between elements that occur finitely and infinitely often. The first one is permutation invariance. This will be accepting the words based upon the letter occurrences but not in any order. Second one is finite versus infinite. This will be distinguishing between finitely and infinitely occurring letters. The third one is resource modeling. This is basically useful for modeling relative quantities of a resources. The third one is K window jumping semantics. In the K window jumping semantics, a word value is accepted if it is by permuting W within contiguous windows of some fixed size K. This semantics is more restrictive and allows specifying properties such as each memory write has a memory read within 10 steps. While this is not more expressive than W regular properties, it is offer more successness. The first one is fixed window size. Extensions allowed only within windows of size K. Contiguous windows. Windows are adjacent and cover the entire word. Restricted permutations. These are the only letters within the same window that can be rearranged. Existential window jumping semantics. This window jumping semantics that accept a word W if there exists some K such that W can be made acceptable by permuting it within contiguous windows of size K. This semantics is a compromise between the jumping and K window semantics. It allows specifying properties like there is some bond such that each memory write has a memory read within this bond. This class strictly contains the jumping languages and gives rise to a new class of languages. The first one is extensional quantification. There exists some windows K, flexible window size. K can vary based on the word and automation. The third one is bounded permutations. Permutations allowed within the chosen window size. Expressiveness of jumping languages. The paper examines the expressiveness of three semantics, jumping languages that are shown to be incapable with W regular languages. The K window jumping languages correspond to regular languages but offer more successness. Extensional window jumping languages are strictly more expressive than jumping languages but are incomparable with W regular languages. The paper provides examples demonstrating these relationships. Jumping languages incomparable with regular languages. K window languages. These correspond to regular languages but more succinct. Window languages. These are strictly more expressive than jumping languages, incomparable with the regular. Closure properties of jumping languages. The paper investigates closure properties of the different jumping language classes. Jumping languages are closed under union, intersection, and complement. Surprisingly, automata in this semantics admit determinization in contrast with the standard automata. K window jumping languages inherit closure properties from a regular languages. For the window jumping languages, closure under union is established, but the paper provides that they are not closed under complementation. Algorithmic properties, jumping languages. The paper will be examines algorithmic properties of jumping languages. These are not emptiness is shown to be NL complete. This is similar to Bushy automata. The lasso membership problem for jumping languages is proven to be NP complete. Containment, equivalence, and universality for jumping languages that are shown to be co-NP complete. These results are obtained by utilizing semi-linear sets and Pressburger arithmetic. First one is non-emptiness. NL complete, similar to Bushy automata. Lasso membership, NP complete for jumping languages. Containment, equivalence, universality. Co-NP complete for fixed size alphabet. Algorithm properties, K window and E window languages. For K window jumping languages, the paper establishes a correspondence with regular languages, which allows for solving decision problems by reducing them to problems on Bushy languages automata. The complexity of these problems may be affected by K. For window jumping languages, the paper proves that the lasso membership problem is decidable, but the proof is more involved and use characterizations of transition matrices in Pressburger arithmetic. The first one is K window languages. These correspond to regular languages, problems reducible to Bushy automata. Complexity dependence. Problem complexity may depend on window size K. The